So, in the last lecture, when we stopped, we given a heuristic derivation of Einstein's equations. Questions are here. Here, what we shall do is we shall start from a, we shall try to give a variational principle and derive Einstein's field equations. And action, so you know that if we want to derive some equations of motion from a variational principle, then we have to start from an action, and that action of the following form. So this is the famous Einstein-Hilbert action. We start uh, the variational calculation from this action. Now you may ask that can you derive this form of the action? If I ask you the question that can you derive this form of the action, what do you say? Is it possible to derive this action? If someone says yes or no. Right. We cannot derive this action, but there are certain things that you should keep in your mind in order to write a good action. First of all, what is the principle on which you can write an action? Huh? That's good. So here, what is the Lagrangian? Can you tell me what is the Lagrangian? What is d4x? d4x, derivative.
Element of
This is the four volume. Right? So what is this? How can you if I want to break it and write it down? What will be this? I am asking this question because I want to know what is the Lagrangian. What is the Lagrangian here? Devanshu? What is the Lagrangian? Root over minus the r. That is the Lagrangian. Are you sure? You are almost right. I would not say that you are totally correct. Almost right. You will get the Lagrangian.
if the dx flow into the time part and space part, that time part and root over minus g r is the last.
Root over minus g
Root over minus g r.
is the Lagrangian density. Why? Good. This you can write it down as this. This is the 3 volume and 2 time. That is the 4 before x. So what is this? This is integral t. X means there is another integration which you do not usually write. An integration. So what is the Lagrangian? So you can write this as BTL is the Lagrangian. So what is the Lagrangian? Lagrangian is integral dq takes this, not root g minus I. So what is this? L is equal to integral dq x times this. So this is basically the Lagrangian density, and it is denoted by a script L. This is capital L, this is script L. This is Lagrangian density. So this you should always keep in mind what is the Lagrangian and what is the Lagrangian density. Now, the important thing is that what are the principles? Are there any principle? You said yourself that you cannot derive this form of the action. We shall vary this action and see what are the consequences of varying this action. But you have said that you cannot derive this form of the action. Then how can you write this form of the action? Is there any symmetry principle on which you have to write, you can write the action? Or what are the principles on which you can write an action? Plausible action. So first of all, what should action be? Can it be a vector? Can it be a tensor of rank 2? Vector is tensor of rank what? Rank 1. Can it be a vector? No. Tensor of rank 2. Higher rank tensor? It has to be a scalar. So you see that it is a scalar. There are no indices. So you cannot write, for example, you cannot write something like this. Not an action. To try to write this is not valid. This is not a valid action at all. What is R? No, what is R? Huh? Ricky scalar. So it is a scalar. So what do you mean by a scalar? Right. It is a scalar. It is a number. So action should be a scalar. So this is a scalar. Before its square root g, this is also a number. Not a scalar. Now the question is, can this be the action? What is the next principle that action should have, or a property that action should have? When you want to write down a valid action, what property should be given? Number one, it should be a scalar. Next property, dimension is always there. You should not write something dimensionally incorrect. That is, see, even your question, root minus g, that is d for x and d for x square root minus g both have the same dimensions. So it is dimensionally not wrong. So it is also a very important point that you should always define dimensions, otherwise it is wrong. Fundamentally wrong. So dimensionally you will describe. But then what should action have? Number one, it should be a scalar. You should write something. See, but what is the symmetry here? What is the symmetry? What is the symmetry of electromagnetism? Remember, electromagnetism you have studied. What is the symmetry? It's very invariant. Very gauge there's a gauge symmetry. So you can show that this gauge symmetry transformation. So if you make certain transformation, this is a gauge transformation. The theory remains invariant. Same for invariant, right? So if a transformation, they form a group. What is that symmetry group? U1 symmetry. U1 symmetry. So abelian group. U1 is an abelian group. You cannot have symmetry because what is that symmetry? If you make certain transformations, then the theory should be invariant. So the action should be invariant after certain set of transformations. What are those transformations? GCT, general coordinate transformations. So these are called general coordinate transformations. Remember, we have always been doing this. X prime is the most general coordinate transformation. These are called what? GCT. General coordinate transformations. Okay? Or diffeomorphisms. This is a name, technical name. These are called diffeomorphisms, and they form a group. So what should be the what property should the action have? The action should be invariant under general coordinate transformations. Now I leave it as an exercise for you to check that it is d4x. This d4x. This is the infinitesimal space-time volume, right? Infinitesimal space-time volume. This d4x is not invariant under GC. It is not invariant under GC. Rather, d4x square root minus g. Please try to verify this. I leave it as an exercise for you to check. In special theory of relativity, by the way, special theory of relativity says d4x is invariant. So you make a Lorentz transformation. So d4x means what? dt, dx, dy, dz in 3 plus 1 dimension. So in special theory of relativity under Lorentz transformation, we have dt, dx, dy, dz will go to dt prime, dx prime, dy prime, dz prime. Apply Lorentz transformation, that will be equal to. So in special theory of relativity under Lorentz transformation, this goes to d. You can write it in this way: d4 x prime 0, like this. That will be equal to 2x under Lorentz transformations. But here it is not Lorentz transformation. It is most general coordinate transformation, TCT. Under those transformations, this infinitesimal space-time volume element is not invariant. Rather, d4x square root minus g is the invariant volume element under general coordinate transformations. And please check it. This is a homework for you. In fact, this is assignment number 1. Please submit this to me by next Monday. Okay. Check it. Do the d4x thing for special theory of relativity, and for general theory of relativity, do it for integrating d4x square root minus. So you can see that this form of the action is invariant under general coordinate transformation. So that is why this is a varied action. You could have said, okay, I can write down other scalars also. For example, what are the other scalars that you can write? See, what is R? You remember what is R? It is scalar. It becomes a Ricky scalar. What is R? You can write R is basically nothing but this, right? This is R. But you could have said, okay, I can construct a different scalar. Why this? You can write an action which looks like this. You always have to obey the general coordinate transformation principle, but you can still write it in this way. ঠিক আছে। But you can always write this RAB, RAB. This is also a scale, right? Like this. What is the other thing that you can write? Is there anything else that you can write? What is RAB? I think we have forgotten what is RAB. Tensor. What is the other scalar that you can form? RP tensor. RABCD. Riemann tensor. RABCD, RABCD. That is also a valid action. So instead of this, you can write something like this. So the choice of your action, you can see that it is not unique, right? You write down many possible actions, but only thing that you should keep in mind is that it should be a scalar and it should be invariant under general coordinate transformations. These are the only principles that you should keep in mind. But what we shall do is we shall start from this one and see what are the consequences of varying this action. So let us try to vary this action. By the way, this is, as I mentioned, this is the famous Einstein-Hilbert action, and it was actually first historically it was first given by Hilbert. So Hilbert gave this action, and Einstein gave the field equations. So what historically, if you see, you will find that Hilbert gave this action, but he never varied the action to find the field equations. But Einstein gave the field equations first. So let us now vary this action with respect to the metric g. So that I shall write it down as delta g. So delta suffix g means variation of this action s with respect to the metric g. If you do that, so this is R. R you can write it down as GAB. Okay. So if you do that, you get three terms. First term is delta, say, let us start from here. The first term, variation of the Ricky tensor. Second term is the second term, so you vary this term, this G or Obviously, there is a invisible G here, means addition is a symmetric G. And then there is a third term, is delta. This delta of this times this GABRL, but GABRL is R, so I'm writing it. These are the three terms that you can have. Good. Let us now concentrate on the first term. Forget about these two terms. Let us concentrate. So let us write down what RAB is. So you know that RAB is given in terms of the Christoffel connection, right? It is given in terms of the gammas. It's a basically symmetry. It's not a tensor, but it's a symmetry. It has a symmetry code. RAB is also symmetric in the. So you know that this has a particular structure. The derivative of one gamma minus derivative of another gamma plus product of two gammas minus product of two gammas. This is the basic structure of this RAB. It's also the basic structure of the Riemann tensor also. So finally, so you have the basic structure, but you don't need to write it. What I shall do, I shall work in geodesic coordinate system. So once again, I shall apply the principle of equivalence. You can do the calculation without going to the geodesic coordinate system. But that calculation is a bit more involved. We can do if we have time, but you don't need to do it also. What you can do is, you can straight away go to apply the principle of equivalence, which is the physics input. And principle of equivalence says that you can always go to a coordinate system where special theory of relativity applies, right? And in that coordinate system, gamma is 0. So if gamma is 0, those product of two gammas is 1, right? And therefore, you can write RAB as, let me write down the expression. I have actually derived this for you many times. Earlier I have derived it, but I would like you to once again check this relation. In geodesic coordinate system, see gamma is 0, but that doesn't mean that the derivative of gamma is 0. That is very important. I will check. Del C gamma C A B minus del B gamma C A C. This is correct. That is why I told you please check it. Check this. Write down. So what you do is write down the most general form of Riemann tensor, contract it. So contraction of Riemann tensor first and third index gives you the DT tensor. DT tensor is there, and then the product of two gammas is one. This is true here. But what do we need to calculate? We need to calculate delta of RAB. So let us do the calculation. This side of the board. Delta RAB. So delta RAB, right? C minus this is what delta RAB is. Straight away take the variation. RAB is this, therefore delta RAB is this. Now we shall assume that the variation and derivative commutes. This kind of thing that we do. Please try to give some argument to prove that indeed the variation and the derivative commutes. So this is your homework 2, this assignment 2. You are doing credit or audit? Audit. So you don't, those who are crediting, please do this and submit this to LC delta comma AB. No, you can prove it rigorously actually. That's it. To prove it, oh, there will be a, sorry. So we have to be careful. Thank you. We have to be a little bit careful. So I will not write it in this way. This, thank you very much. Now it is fine. So you have two terms. Because now what we shall do is multiply, see this thing multiplied by GAB. So we will just multiply GAB. This is all standard calculation you will find in the books also. But what you will not get, Weinberg does this thing this way. As far as I remember, GLC coordinate system. But as I mentioned, you can do it without integers. But doing it and then you can vary and you get the same answer. But here also there is a subtle point which I shall mention. The finish of the calculation that is not as usually mentioned. So if you multiply GAB by this delta RAB, so what you will get now is GAB C C C minus so what we have done is we have plain and simple multiplied by G. Now once again apply the principle of equivalence. So what you can do is replace this del C and del B by covariant derivatives. Why? How can you do this? Because gammas are zero. Gammas are zero. This thing by covariant derivative. And then, so you are applied the principle of equivalence 2 times. Now you apply the principle of equivalence once more. See, we have shown in the earlier lecture, principle of equivalence is equivalent to saying that the metric has obeys a particular property. This covariant derivative of the metric is zero. So that is metric compatibility. What you can do is you can put this here. The second principle of equivalence, metric compatibility. Because covariant derivative of the metric is zero. Right? So you can put it inside the derivative. So so far in our discussion, I have given you 3 assignments. Please remember, I have asked you to check this one, very important general coordinate transformation. Check this one, it is a small assignment, small thing, and check this other check that and the variation comments. So please check these 3 things. The very small things will not take much time. So this is what we get, and now what we can do is, so remember that we are only calculating this term. There are 2 more terms that we have here. Let me just remove it. The next part we shall calculate this term, the last term. This we don't need to calculate, do any calculation. Second term. So what do we have? We have GAB delta R equal to grad C. Let me just check and say. So this I shall call C, because here you can see that AB are the lamines, they are contracted, the field index is C minus grad B. And this, so here you can write this down as, so what you can now do, B is the dummy index, we can change it to C, change it to C, where C on the index, C small c, defined as AC minus. What is AC? AC is this thing. What is BC? BC is this. So what you can do is you can replace this C by B, this B by C. So then this will become grad C, BC. So these are all the delabelings. Okay. So now what we need to calculate, therefore, is the following integral 4x square minus g. This was delta R A B. Uh, so delta RAB GAB, that is this thing. This is equal to okay. Is it fine? So what we have shown is that first term, first integral is basically equal to this. Now you can show this is this. Once again, I repeat, this is capital C. This is not index. This small c is the index. Then show that covariant derivative of some vector, this is contracted. So this good thing is a scalar, right? This is equal to this. This is assignment number 4. I shall show you one of the steps. I shall show you one identity. I shall put one of the identities. Using that identity, I have prove this. Prove that grad A is del A square root minus G A A. This is assignment number 4. So I will not bother you with any more assignments. So these are the 4 assignments which you will submit by now. So from this, you can immediately see that this factor and this factor cancels, right? Therefore, this integral is nothing but 3/4x del C C. And what is CC? This is AC minus BC. And you know what is AC and BC? AC is this thing and BC is this thing with proper labelings of the indices. So what about this integral now? Can you do this integral? Yes or no? See, the first term has simplified to this. Can you do this or not? Devanshu. Devanshu, come, any suggestion? Have you seen these kind of things earlier? Done classical field theory. Not done classical field theory. No, course. You're not done classical mechanics. So have you done this infinite spring model? Your masses connected by massless springs, one-dimensional chain, where each of the masses connected by springs is separation is small k. That is the point. So to start by writing down the Lagrangian of such a system, which you have done in quantum physics, solid state physics or whatever. You can also do it in classical mechanics. Now, if you take this A going to 0 unit, the separation between the two masses connected by massless springs, infinite chain of that. To take separation, the separation A going to 0. What is the model? What is the theory that you do? Have you done this? Anyway, if you had done this, then you would have encountered these kind of these kind of theories. See, it is not that you have not done classical field theory. You have done classical field theory. Where? Give one example that you already know of classical field theory. Electromagnetic, electrodynamics is a classical field theory. You have done classical field theory, and you must have studied this kind of things. So this is also a classical field theory. The generality of relativity is also classical field theory. So you must have encountered integrals like this in electrodynamics also. Not encountered. Sure. See, what is this term inside? There is C of something. So what do you expect to get if you integrate this? Will come. Then? Acha. Follow. Divergence theorem. Gauss divergence theorem. What is that theorem? I'm given a theorem. Vector notation. I will. Gauss divergence theorem. But now, how can you write it in a more modern notation? This is basically the notation of vector calculus. Can you write them in a more modern notation? You can write this down as. What about this? What about this? Huh? What about this? Become AI? NI? Huh? Right. AI NI? DS. There is a DS, hidden DS. So what you can write down as this is DSI. So this is the modern notation of writing down the Gauss divergence theorem that you have learned already. But here it is something different. What are the values that I can take here? 1, 2, 3. So 1, 2, 3 are what? Special indices. But here C, what are the values that it can take? 4. 0, 1, 2, 3. So it is a little bit different. So here you have to apply, this was the 3 Gauss divergence theorem. This is the 4 Gauss divergence theorem. This is the 4 volume LC. So better way to understand is that this is a total derivative. The total derivative term, and therefore you can write this term as this is the free surface, right? So once again, this is an extension of this of the Gauss divergence theorem that we learned in vector calculus, and you can write this down. This is the free surface which encloses the fourth volume, the fourth space-time volume. Right? What should this be? What should this be equal to? One should. What do you should? Account लिखते चले. dx dy dt को dx dy dz dt. That is equal to x. Now this is d sigma c. It is a free surface. It encloses the four volume. Now এই ইন্টিগ্রালটা কি করে? কি করে? ভলিউম ইন্টিগ্রাল কে আমরা সারফেস ইন্টিগ্রালে কনভার্ট করি। ভলিউম ইন্টিগ্রাল কনভার্টেড টু সারফেস ইন্টিগ্রাল। ইলেক্ট্রোডাইনামিক্সে কি করি আমরা? দুটো বলে দিতে ভালো বলে করি। ভলিউম ইন্টিগ্রালে সারফেস ইন্টিগ্রালে কনভার্ট করে আমরা তারপরে কি করি? এই ভলিউম থেকে এই সারফেস ইন্টিগ্রাল করে জাস্ট রিকল ইলেক্ট্রোডাইনামিক্স কি করা হয়? সারফেস ইন্টিগ্রালে নিয়ে যাই টাইম
charge
we say that the fields the surface টাকে আমি infinity তে নিয়ে চলে take the surface to infinity and we say that the fields vanish at infinity and therefore this term is equal to 0. Here also in general theory of relativity, because see the first term under variation gives you some boundary term. This is the boundary term. It is surface term. এখন অন্য দুটো টার্ম ক্যালকুলেট করি নিয়ে I can calculate the other two terms. The first term is a boundary term, and the other two terms we shall calculate, right? And from that, what is our aim? Our aim is to find out the equations of motion. So what shall we do? We shall apply the principle of classical mechanics. We shall apply the principle of least action. We shall say that the variation of the action is such that it is zero. It extremizes the action. The variation of the action under with respect to the matrix such that it extremizes the action. That is the principle of least action. So we shall impose the condition that delta G S H is 0. This is the physics input that we shall put later. And from that input, we shall, our aim is to get the field equations of general relativity. The problem is that there is a boundary term. Unless you make the boundary term 0, you cannot get the equations of motion. You have to make the boundary term equal to 0. That is what happens in ordinary classical mechanics also. Right? You start from some Lagrangian, S is equal to integral L dt, vary it with respect to the coordinates, with respect to x, and then what you say? The variation of the action with respect to the coordinate q, say L is a function of q and q dot, you vary it with respect to q. Then you get some term, some bulk term, and some boundary term. The boundary term you say that the variation of the q's at the boundary is 0. Then you get the Euler-Lagrange equation of motion. Here also it is the same. So you have to get rid of this boundary term. Otherwise, how will you get the Euler-Lagrange equation of motion? Not get it. So you have to make this 0. And the argument here is that these variations. What is CC? CC is nothing but this minus this, right? The variation, you say that variation of gamma at the surface is 0. Okay? So if you impose that, then your first term this is equal to 0. Variation of gamma at the surface that you have at the boundary is 0. But there is a catch when you come back to it. Please remember this point. I am saying that the variation of gamma at the surface is 0. Why I am doing it? Because I have to get rid of the boundary term in order to get the Euler-Lagrange equation of motion. Okay. I will give you one more assignment. Small assignment. So let us now concentrate on the third term. Second term I mentioned, the first term is 0, it's 1. Let us concentrate on the last term. What is the last term? Let me write it down. The last term is d for x square root minus g delta of this times square. Right? This was the last term. The assignment that I give you, this is the fifth assignment. Please show that this variation of this matrix square root minus g is minus half is GAB. Okay. This is delta of g square root minus g is equal to this try to do it. So if you prove it, like if some little effort you will be able to prove it, then you can see that we have actually calculated everything now. So delta of SEH, the first term on the by the variation is a boundary term, and by the demand that we have made, the first term is 0, right? And what are the other terms that you have? Other terms are 4x. Second term that is 0 plus 12 minus g RAD delta GAB, right? This was the second term. We don't need to do any calculation. This is as it is. Leave it as it is. What is the third term? Third term also has a square root minus g. So I just take it common, and before is obviously there. You can just put a bracket minus half GAB. This thing is equal to this thing, but then you have multiplied by capital R. Okay. R here, and delta GAB is also here, right? Delta GAB contravariate. So you can take delta GAB also from. The final result is delta G of Einstein-Hilbert action is d for x square root minus g of this thing delta GAB. Right? What is this thing? Capital GAB, which is the Einstein density. You know that this is covalently conserved. That is the Bianchi identity. So now, as in classical mechanics, this term I call it with a bulk term. Bulk term. Because this is the volume integral. And surface term, we have got rid of it by imposing appropriate boundary condition. Now you impose the last physical input that you have already learned in classical mechanics, principle of distraction. You impose that this variation is 0. Delta GAB is arbitrary variations of metric. Therefore, the only way by which this can be equal to 0 is that capital GAB must be equal to 0. So these are the Einstein field equations of general theory of relativity in vacuum. Why do I say that this is vacuum? Because there are no matter fields here. That is why it is vacuum. And this equation is obviously consistent because if you take a covariant derivative of left hand side, it is 0 identical. 0 is equal to 0. It should be consistent. That is why everything is fine. GAB is equal to 0. We know that covariant derivative of GAB is equal to 0, but the field equations in vacuum says that the Einstein tensor is itself equal to 0. Is it okay? Does it become? Any questions? If you want to ask any questions, so I hope you have written down all the assignments. If you have any questions at this point, you can ask me. No questions. Any simple question, whatever is in mind. So please remember that these are the Einstein field equations of sphere. Vacuum. There are no matter fields. Vacuum because matter fields are absent. Okay. I will get back to the boundary term once again, but before that, let me do a small exercise. So GAV is equal to 0. These are the equations, field equations of gravity in vacuum. So to write it in longhand, this is basically vacuum Einstein field equations of gravity. What we do is contract this equation with GAV, contravariant GAV, both sides. Right? So if you contract, what is the first term? Very good. This part is R. GAV, এটা কত? Huh? GAV contraction. It's also a number. What is that? She said 1, 4. So it's 4. We get is R minus half. GAV is 4. Please show it. Assignment number 6. Please show it. R is equal to 0. Right? What is this? 2. So what do you get from here? Keep enough. Keep enough. It is equal to 0. তাহলে কি? হ্যাঁ? এটা বলো। হ্যাঁ? X এটা 0 তো বলো না সেটা বলতে কি আছে? So R is equal to 2. So what we have shown is that Einstein field equation, vacuum Einstein field equation. If the Einstein field equation is 0 হয় তাহলে Ricci scalarটাও 0. তাহলে Ricci scalarটা 0 মানে it is basically identically 0. It must be 0. Right? So এই field equationটা কি তাহলে আরো সিম্পলিফাই করে যায়? Does it simplify further? Simplifies because this term is not there. So this is equal to 0 implies AB is equal to 0. So these in vacuum, the actual field equations of GR is RAB is equal to 0. And you remember that we derived it heuristically from the geodesic derivation equation and applying the Newtonian limit and whatever. Give a derivation in vacuum, we show that RAB should be equal to 0. So field equations of GR in vacuum is equal to 0 implies RAB is equal to 0 because R itself is equal to 0. Always remember this. And our aim in the future lecture will be to solve this equation. Try to solve this equation and see what do we get. How many, by the way, how many equations do you need to solve? RAB কটা component আছে? A symmetry কটা আছে? 10টা. We have to solve 10 differential equations. And RAB মানে you know it is derivative of gamma মানে gamma হচ্ছে derivative of g. তার মানে these are basically second or double derivative of the metric tensor. So you have to solve 10 such equations. So you can see how difficult it is already, right? we find that you can get a solution of this. It's something remarkable that you get a solution of this. Okay. Let us now come back again. Let us come to the boundary term. What was the boundary term? Please remind me. Please tell me what was the boundary term. The boundary term was equal 12 minus d cc. cc টা কি ছিল? cc টা হচ্ছে ওই factor like that. It is GAB delta gamma c minus g. এখানে we have to be careful. b টাকে c করে দিতে হবে, so it will be GAC delta gamma c টাকে b করে দেব. This, as I mentioned, this is the three surface which encloses the four volume. So we had applied the four Gauss divergence theorem. This was the boundary term. This is the boundary term. And in order to get the field equations of GR, we had to impose the condition that the variation of the crystal connection has to be zero on the boundary. But the point is that usually it is stated like this in the books, that this is a standard calculation that is done in the books, and where you need to impose the fact that the variation of the crystal connection is zero on the boundary. But this is wrong. And you say why? It's actually not correct. This is incorrect. This is the catch that I mentioned. So I saw that you were smiling at something. You thought that that was the end of the story. It's not the end of the story. This thing is actually not correct. That is zero kореchi, but I have cheated. The cheating. It's cannot be correct. এইটা জিরো করতে হবে। সি আমরা ক্লাসিক্যাল মেকানিক্স নাও কি করতে হয়, ডেল্টা কিউ টাকে at initial time pi and final time ts, so delta q at pi is equal to 0, delta q at tf is also equal to 0. That gets rid of the boundary term in classical mechanics, and from there you get to Euler-Lagrange equation of motion. Here also you need to get delta gamma of this to be equal to 0 on the free surface sigma c, but that is a problem. You cannot do that. It's a problem because it does not give you a well-defined boundary value problem. Why? What is gamma? Gamma structure is G and multiplied by derivative of G. This is the generic structure of gamma. Now if you take delta gamma, that will be delta of this thing, and this will give you two terms, delta G, del G, plus G, del of delta G. Sorry, delta of del G. Right? Two term like this rule problem. But you can, you know that delta in derivative forms, that was one of your assignments. So you can write this as delta. This I have applied one of the results from your assignments. So if you demand that delta gamma, the variation of the crystal connection on the free surface sigma c is equal to 0. By the way, this free surface is already a hypersurface, right? Because free surface means it is embedded in four volume. The hypersurface. You cannot visualize it. You cannot visualize. You can always visualize two-dimensional surfaces. For example, plane. Here, these are three surface means it's a hypersurface. So this, we demanded that this is equal to 0 on the free surface. But if this has to be 0, then you have to demand that variation of the metric is 0 on the surface, on the hypersurface, and the derivative of the variation of the metric is also 0 on the surface. So you have to impose two conditions. Imposing two conditions does not define a well-defined boundary value problem. What you can do at most is you can at most say that okay, delta G vanishes on the surface. Delta G variation vanishes on the surface. It's a well-defined boundary value problem. Therefore, delta Q is equal to 0. Or you can say that okay, the derivative, the first derivative of the variation of the metric that vanishes on the surface. যে কোনো একটা তুমি করতে পারো কিন্তু এখানে দেখা যাচ্ছে একটা করলে it is not sufficient because if you put one condition one of the terms remain তার মানে boundary টা তো পড়েই থাকছে equation তুমি পাচ্ছ না it's not a well defined boundary value problem but usually in the books it's done in this way which is actually not correct but here if you do this little bit of cheating then it's fine you land up with Einstein field equations and everything. So this was a catch that I wanted to mention. What is the way out of it? Can you tell? সবই ঠিক আছে এখানে কিন্তু একটা মেজর একটা ফ্ল আছে যেটা নিয়ে লোকের মাথা ঘামায় না মাথা ঘামানো উচিত because in general theory of relativity boundary terms are very important. Such a theory is highly non-trivial theory where boundary terms should be treated very carefully and you have two terms, you can impose only one of the terms, one of the variations to be equal to 0, not both variations. And what is the way out? কি হতে পারে এবার আমি অনিশ্চয় জিজ্ঞেস করবো বা আমি করতে what is the way out? এটা তোমরা পারবে না ইন্ডিপেন্ডেন্ট রিলেশন দিলে তো হয়েই যেত সেটা পারবে দেখো the problem is that technically speaking mathematically speaking boundary terms are very to get a good boundary value problem যদি এটা শুধু করো তাহলে it is not sufficient there is a problem here যে প্রবলেমটা ইউজুয়ালি বলা হয় না আইনস্টাইন হিলবার্ট অ্যাকশন নিয়ে করা ভ্যারিয়েশন করে আইনস্টাইন ফিল্ড ইকুয়েশনস অফ মোশন provided that this boundary term is 0 that is you impose that this is 0 on this is surface but this 0 means delta g is 0 and derivative of delta g is also 0 কিন্তু একসাথে 0 করা করলে ঝামেলা আছে তো একসাথে 0 করলে ঝামেলা আছে সেটা করা যায় তাহলে উপায় কি উপায় একটাই উপায় হচ্ছে আমরা স্টার্ট করেছিলাম কি দিয়ে started with the fact that following actions right this is the famous Einstein Hilbert action mind you Hilbert কিন্তু এটাই লিখেছিল Hilbert he was a great mathematician considered to be one of the greatest mathematicians of the 20th century action একটা এক্সট্রা টার্ম অ্যাড করতে হবে সেই টার্মটা কি হ্যাঁ হ্যাঁ ধরে we have to know that is difficult to find actually but you can find it it's not that difficult also basically you have to add some term whose variation will cancel one of these terms এমন একটা টার্ম অ্যাড করতে হবে অ্যাকশনে যার ভ্যারিয়েশন দিলে এর মধ্যে যে কোনো একটা টার্ম আমি ক্যান্সেল করে দিতে পারবো এবং আমি কোন টার্মটাকে ক্যান্সেল করতে চাই আমি মেট্রিকটা ভ্যারিয়েশন অন দি সারফেসটাকে 0 করব so our aim will be to cancel this term such a term add such a term in the action such that the variation of that term will cancel this term and what would be the nature of this term এই টার্মটার নেচার কি হতে হবে এই টার্মটার নেচার it has to be a boundary term the surface term কিছু add করতে হবে actual to get a good boundary value problem in general theory of relativity which is Einstein Hilbert action is not sufficient so Instant Hilbert action is the bulk term. Bulk can why bulk? বলেছি আগে bulk can. বলেন before it's the bulk term একটা boundary term আছে. You have to add a boundary. And the fact, see, Hilbert gave this, right? And Einstein gave the field equation. And later on, historically, এটা অদ্ভুত হিলবার্ট আগে দিয়েছে কিন্তু আইনস্টাইন হিলবার্ট অ্যাকশন করা এটা অদ্ভুত হিলবার্ট আইনস্টাইন অ্যাকশন বলা উচিত বা হিলবার্ট অ্যাকশন বলা উচিত আইনস্টাইনটা দেয়নি but when Einstein found when he himself did the calculation he saw that there is some flaw here the flaw is this thing is a problem so he added a boundary he added some boundary যে টার্মটা আইনস্টাইন অ্যাড করেছিল সেই টার্মটাকে বলা হয় আমরা সময় থাকে এই ক্যালকুলেশনটা করে আমি দেখাবো বাট আই ডোন্ট থিংক whether I will get time or not this is called the Einstein boundary term you add an Einstein boundary term here which Einstein himself noticed that there is a problem if you add some term here then the variation of this term this boundary term with respect to the metric cancels this term. And now, to get rid of the surface term, you just need to say that the variation of the metric on the surface is zero. That is a perfectly well-defined boundary value. No problem. So Einstein added this boundary term. So this is the full action of GR. Because later on, the boundary term that we can actually use that follows identically. But there are some problems with this boundary. There are some other more technical problems. Later, further boundary term was suggested because derived sort of derived, and it got rid of the problems that this Einstein boundary term has. And that boundary term is said to be the GHY boundary term after the name of these three people, Gibbons, Hawking, York. So this, I will not write down the form of that term. You can basically write it down. It's not nothing. It's basically some surface term. Then, so this is the induced metric on the free surface, and this is the extrinsic curvature. We have learned what curvature is, not curvature, heat itself. The extrinsic curvature. We have some free surface here. This term is actually called the Gibbons Hawking York term. They gave much later. Much later, you can understand that Hawking's name is there, so this was given much later. So the full action of gravity is Hilbert plus Gibbons Hawking York term. Sometimes you add some more terms. That is not due to this problem, but to tackle some divergence problem. And that is always there in field theories. If you want to cancel divergences, you add a further term in the action, and those terms are called counter terms. But we don't need to worry about counter terms here. Just remember that the full action of gravity is this action plus some boundary term. While doing this boundary term, get a well-defined boundary field. Otherwise, it's not a well-defined boundary field. And not only that, not only well-defined boundary field, these boundary terms are very important in general theory relativity because they contribute to physical processes. You can show that they are physical effects. It is not something unphysical that you are doing, or it is not something mathematical that you are doing. It is a physical effect also. The boundary term is very important. When you calculate black hole entropy and things like that, there is a formalism by, I think all of you have heard of Professor Shish's name, right? He has a formalism to calculate entropies of extremal black holes, supersymmetric extremal black holes in string field. Those black holes which come from string field. And you can calculate by some, he has developed a formalism which is called the entropy function formalism. That formalism, by using that formalism, he is able to calculate the entropies of those supersymmetric extremal values that arise from string theory. In that formalism, these boundary terms play a very important role when you want to calculate the entropies of black holes. So it is not something unphysical, it has a physical effect. Anyway, so I would like to stop, I would like to take a pause here and take some questions if you have at this moment. As I mentioned that in the future, our aim will be to solve this equation. Which are a set of nonlinear differential equations, 10 of them, second order. We will try to solve these equations. Any question that you have in your mind? The one should be question. And it's an informal discussion. Right? Annual. Annual is solved. It's a good question. First of all, we should not be afraid of this. It's a very nice question. তুমি ভাবছো হাতে কি করে সলভ করছো এটাই তোমার কোশ্চেন প্রথম উত্তর হচ্ছে হাতেই সলভ করছো হাতেই করছো কারণ এই ইকুয়েশনটা যে সময় সলভ হয়েছে তখন কম্পিউটার দিয়ে সলভ করার কথা মানুষ ভাবতেই পারে এখন তুমি কম্পিউটারে সলভ করতে যে সময় সলভ করেছে তখন কম্পিউটার দিয়ে সলভ করার প্রশ্নই নেই তাহলে এটা হাতেই সলভ করছে দ্বিতীয় প্রশ্ন যেটা তোমার মাথায় আসা উচিত আইনস্টাইন নিজে সলভ করেছে আইনস্টাইন নিজে এটা পার্সিয়াল সলভ করেছে কথা হচ্ছে আইনস্টাইনের কমেন্ট কি ছিল বা বক্তব্য কি ছিল এই ইকুয়েশনটা রেখে আইনস্টাইন নিজে বলেছিলেন যে এই ইকুয়েশনটা সলভ করা যাবে so he never he was of the opinion that this equation অনেক কিছু এক্সপ্লেইন করে কিন্তু এই ইকুয়েশনটা এক্সাক্ট সলিউশন হয়তো বার করা যাবে কিন্তু এক্সাক্ট সলিউশন ইন্ডিভিজুয়াল আর্টিফিশিয়াল বার করছে এটা বলে আর রিলেটিভিটি প্রপোজ করেছে 1915 সালে প্রপোজ করেছে 1915 আর শর্টসিট সলিউশন দিচ্ছে 70 না 1960 maybe 16 or 17 or 18 because now they বছরের মধ্যে সলিউশন পেয়ে এক্সাক্ট সলিউশন what are the approximation exact solution maximum if you do for the exact solution for it. It's a good question. So if you have questions like this, please ask the important questions. So our aim will be to solve this equation. That is our next aim. If you have any further questions, then also you can ask. Otherwise, we shall proceed. বলো এবার আমরা নেক্সট যেটা করব সেটা হচ্ছে I give you one of the assignments, right? I will prove simple identity using which you have to prove a further identity. কোন আইডেন্টিটিটা মনে করে দেখো which identity? The covariant and basically the covariant divergence of the code. Grad A in A. That is what? What the code divergence? কিসের ai ai হলে কি হতো কোন ডাইভারজেন্স এর এ যদি এইটা লিখতাম এটার মধ্যে তফাৎ কি তাহলে এটা কি এটা ফোর ডাইভারজেন্স of a four vector ordinary four divergence the four divergence covariant divergence and this say that this is equal to this was the thing which I gave you to prove it was one of the assignments to prove it this is identically true before that before proving it I shall show one identity for you using that it will be just one or two lines with this one. So let us prove the following. Let's take gamma A B C. This is basically half A B. B. D. Plus del C H C minus A G. So we start from this thing. And what you do now is okay. This is equal to take it as A equal to A equal to. So this is also A. A, B. So this term, first term, you can write it down as half GAB del A. Write this down as right. That's take it to level. Last term na minus del A. Second term like what I mentioned is now right. Now here you can immediately see that it cancels, right? Because D টা তুমি A করে লিখবে D টা dummy units. So this is basically nothing but equal to half A D D is equal to this. Okay. So if this is okay, then remember that I gave you the proof formula like this. Delta of this is equal to something. So in proving that formula, we get require another formula which is delta G equal to প্রমাণ করতে গেলে লিখেছিলাম equal this one. So you need to prove this also in some sense. To prove it. If you can prove this, you will be able to prove this immediately. Just Barche. Coming closer to the board. Yes, so I'm happy in some sense, but to be very interested by yes. Very yes. Okay, George would interest by each year. Okay. So please try to prove this. So if you are able to prove this, you can see you can immediately prove this. This is one line. Because if you know that, you will be able to prove it. Now, delta G, you take delta XC, say, so that is equal to G, G, the so you can write this as 1 by G. 1 by G, there is delta G, delta XC. Now you can do another trick. This you can write, right? Similarly, this like this. ঠিক আছে? Eta actually same because this D is a dummy index, I can replace it by D. Right? So what is GAB? Del C GAB is the that is equal to 1 by G del C G. You can replace this by half G. ঠিক আছে? By the way, what is G? Theta কি? Theta বলা হয়। Sorry for that. What is G? বারবার G লিখছি, ঠিক আছে? ওই যে d for x square root minus G লিখেছিলাম। Square root minus G, G টা কি? হ্যাঁ? It is the determinant of that GAB. GAB का metric कैसा है? बेटा क्लोजर कोड मैट्रिक्स, सिमेट्रिक मैट्रिक्स, वही मैट्रिक्स का डिटरमिनेंट হচ্ছে G। তাহলে হ্যাঁ একটা আরেকটা জিনিস তোমাদের জিজ্ঞেস করা উচিত ছিল যে গুড পয়েন্ট স্কয়ার রুট মাইনাস d কেন দিয়েছিলাম why was it minus square root of minus d because the determinant of G the metric answer is the minus আসবে determinant is the minus আসবে because it is there's a Lorentzian signature then it will have a minus if you take the determinant of that so তুমি যদি d for x square g নিবে তাহলে অ্যাকশনটা হবে না ইমাজিনারি হবে So another property that we should have, the action should be a number and it should be a real number. It should be a real number. So that is why you have to put a square root minus g to get rid of the sign. Now it is positive. Square root minus g is a positive number. So square root is a very it is also a positive real number. I will not take the negative real number. Positive real number and then everything is fine. So this was a point that I missed when I discussed the Einstein-Hilbert action. Now it completes. The discussion is complete now. So here also see, you see that G is a determinant of that metric tensor, but this is negative, right? If I want to make it positive, so is a negative positive plus like this, the minus G, and you can write this now down as half ln of minus G. This log of minus G and del C of this. Yes. The derivative of log of minus G is 1 by minus G del C of minus G. Okay. Now we can put this half here, using the property of logarithm. Therefore, this becomes del C log of square root minus G. So gamma A del C of log square root minus G, where G is basically the determinant of the metric tensor. This is a negative quantity, but minus G is a positive quantity. So this is an identity, it follows identity. And proving this identity, you are required to put this one, which will prove one of your assignments. And using this identity, you now need to calculate what is this thing. You have to use this. So you will be able to prove the other assignment. This is a two-line proof. ঠিক আছে যোগ চাওয়াচাওয়ি করছে তখন তাহলে I will get bored of it and I will stop here for today. But energetic enough to clear around. আগের দিন তো মনে করেছি এটা যেন না হয় that should not be with anyone, not with any factor. আগে ইনফর্ম করে দিলাম কিছু বলবেন remember that here now if you feel you should feel free that okay sir all of them bus is here then you can stop here. If you have some little energy then I will maybe carry on for another 10 minutes. The last exercise for let us stop here for today and then we shall carry on from here on the next class. The next বুধবার অর্চন স্যার ক্লাস নেবেন তাই তো অর্চন স্যার ক্লাস নেবেন তো আরে আমার ক্লাস আবার নতুন নিয়ে আমরা আমাদের ভালো প্রবলেম ফ্রি আছে তাহলে সেদিকে আমি আগে ক্লাস নেব তো আমরা এখন পর্যন্ত what we have learned is the heat equations of GR gravity in vacuum. But what about if we have matter, right? So if we have matter, then this full action of gravity will be equal to the Einstein-Hilbert action. Einstein-Hilbert action is pure gravity, matter means it is pure gravity plus matter action plus some action for matter fields. Second, this is equals square r. I told you why square root of minus g. The determinant of the minus is to get a positive square root, such that the action is a real number, and then you have this. This will be not. Well, Einstein boundary term. After the forget about it. But I just wanted to tell you that you should be careful here. But for the time being, obviously you are correct. I should add a boundary term. I have not added. So when I am not adding a boundary term here, basically I am cheating. Not correct. This is the matter term. This is the matter Lagrangian density. So that is why I have not written it as capital L M. Rather, I have written it as a split L M. This is a Lagrangian density for matter. It can be any matter field. For example, it can be radiation fields, it can be some fermionic fields, some bosonic matter fields, whatever. Radiation is always obviously the bosonic field, but it is say like it is something different from matter because from less than zero. But anyway, radiation. We shall do the radiation case in the next class. হ্যাঁ প্রথম ফার্মিয়ন মানে কোয়ান্টামে ঠিকই কোয়ান্টামে চলে যাচ্ছে তো কারেক্ট ইন সাম সেন্স বাট ঠিক আছে ইউ গেট ফরগেট অ্যাবাউট বোসন এন্ড ফার্মিয়ন রেডিয়েশন এটা আমাদের অত্যাধিক নলেজের প্রবলেম যে প্রবলেমটা ধরো আমার দিকেই আমি বললাম রেডিয়েশন ফিল্ড আমার বোসনিক না হলেও চলতো but you can put radiation fields like right you can put along with gravity you can put classical electrodynamics. And you know that when you quantize electrodynamics, the quanta are photons, which are bosons. So now you have this term. And let us again do the variation. Huh? This is basically kappa. The chaos. Kappa. This is a coupling constant. কি হচ্ছে এখানে matter field is getting coupled to gravity. So here this is some sort of gravity যেটা আছে এখানে তোমার matter is getting coupled to gravity by some coupling constant kappa. And then we will some matter classical fields. তাই জন্য আমরা জিনিসটা আরো কঠিন তার মধ্যে লিখে দিতে পারবে না আমরা একটু যদি সেগুলো ফিল্ডস হয় তাহলে তুমি ছোট করে লিখতে পারবে না তো কাজ আছে লেখা কাজ আছে তো মন্দিরে জিজ্ঞেস করছে যে এখানে তো ফেরমিয়ন বোঝন মানে তো এটা তো কোয়ান্টাম স্ট্যাটিস্টিক্স ফেরমিয়ন বোঝনের আইডিয়াটা কখন আসে ইউ আর ডুইং কোয়ান্টাম স্ট্যাটিস্টিক্স সো কোয়ান্টাম ব্যাপারটা কি তো এটা দিস ইজ অলসো গুড পয়েন্ট because you can actually put bosonic fields here, fermionic fields here, but then a sort of hybrid type of জিনিস. Gravity is classical, matter fields are quantum. That you can do. So you can treat matter fields in a gravity pattern. So basically, যখন এটা করা হয়, we are basically trying to do quantum field theory in curved space-time. আমরা quantum field theory in flat space-time করি usually. যখন আমরা classic quantum field theory, when we learn quantum field theory, what we do is we learn it. We learn quantum field theory, that is fields, matter fields, which are quantum in nature. They are in a special theory of relativity value. So that in flat space-time. But when you do quantum field theory in curved space-time, it is something different. And then you have to start from this one. So now our aim is to vary this action, respect to the metric G, and impose the principle of this action to find out the equations of motion. That is our aim. If you do that, এই পার্টটা আমরা অলরেডি করেছি। এই পার্টটা what does it give? It gives us GAV, delta GAV that. You only need to find out this part. Let us do that. So let us start from that part. So you are wanting to calculate delta G of SM, the matter part of the action. That is for X. This kappa, the coupling constant. Delta upper square root G ln plus two terms. So you can see the assignment that I gave you arises again and again. So you need to do this assignment. It's very important. So this you know what is the result? You already know. You only need to get this one. So this delta n this. And delta of square root minus G, that is minus half check করে নিয়ে একবার minus half GAB delta GAB at the square root minus GAB. So this variation is basically equal to this. So now we have combined both of these. I have a bracket আছে আমার মনে নোট খাতা ঠিক করে bracket আছে হ্যাঁ একটা আবার কি আছে না ওটা কনস্ট্যান্ট কাপলিং কনস্ট্যান্ট ওটা ভ্যারি করতে পারে এটা কনস্ট্যান্ট so this is equal to kappa integral d4x minus g এটাকে আমি এরকম ভাবে লিখেছি কপি করে লিখি delta ln do not write it like this but I am being a bit sloppy placing this like this minus half the G extra values. আমি তো একটা জি এক্সট্রা লিখেছি, এই জিটা স্কোয়ার রুট এই জিটা থাকবে minus delta square root minus g, that is minus half gab delta gab square root minus g. Right? There is no g there. It's minus half square root minus g gab delta g. Okay. So you get this thing. এর সাথে কি যোগ হয়ে আছে? এর সাথে তোমার আছে হচ্ছে এটা so this plus this thing is equal to 0. Delta g is common. Then take it outside. Therefore, what you get is gab plus kappa times equal to 0. Because for arbitrary variations, the only way that you take that variation, this thing can be equal to 0. Total thing, variation of the total action is equal to 0. Half g, is equal to 0. Now, I will define something. Where PAB is minus of this. Definition. This is the energy movement, stress energy tensor. So you see that we have derived everything by adding matter, action, the instant field action. We are able to derive field equations of general relativity in the terms of matter. We need to calculate the stress energy tensor for matter. What is the coupling of matter with gravity? How can you fix it? The only way is to go to the Newtonian limit, and it will be what is kappa? The final equations is kappa. Basically, this answers your question. Given variation, G is the Newton's universal constant of gravitation. C is the speed of light. So G capital GAB is equal to kappa PAB. PAB is the energy moment tensor. Kappa is 8 pi G by C4. The coupling constant. And from this equation, you can see that the left hand side is purely geometry of space-time. The right hand side is the matter sector. So basically, roughly Einstein field equations of gravity is basically equal to geometry is equal to matter. So gravity tells matter how to move, and matter tells space-time how to curve. So it is kind of a feedback kind of equation. So this tells this how it should move, and this tells this how it should curve. It's a feedback loop kind of an equation. In the next lecture, what I shall try to do is that I shall add the radiation field, the Maxwell field here, try to calculate the equation, full equation of the Maxwell field. And this is one of our names, and another name is to calculate or to find the solution, the exact solution of RAD is equal to 0. These are the two things that we should do. So let us stop here for today.